about machine learning. So machine learning, so these are using neural networks to predict answers to various questions that you can use in many ways. I think I'll skip the first way I was discussing it, which is to use neural networks to guess solutions to partial differential equations, which is a very exciting new tool in PDE, but I will skip it. I would instead talk about another application of machine learning to knot theory. So knot theory is quite a fun area of mathematics. It's an interesting area that it brings together many different fields of mathematics, and they don't really talk to each other. So a knot is just a loop of string or a curve, really, in space that is closed. And two knots are equivalent if there's some way to continuously deform one knot to another, which in a way in which you're not allowed to cross, the string is not allowed to cross itself. Okay, and so the basic questions in knot theory are, when are two knots equivalent? Okay, if I give you two knots, is there some way to turn one into the other? And the way you approach this question normally is that you develop these things called knot invariants. So these are various numbers, sometimes also polynomials, that you can attach to a knot, and these numbers don't change no matter how you continuously deform the knot. So if two knots have different invariants, they cannot be equivalent. So there are many types of knots, of invariants. There's something called a signature, which sort of counts, you flatten the knot and you count crossings, whether the crossings go over or under, and you create a certain matrix and so forth, and there's a certain integer called the signature, so that is one type of knot invariant. There's some famous polynomials called the Jones polynomial and the Helmholtz polynomial, which are connected to many areas of mathematics, but I won't talk about. And then there's these things called hyperbolic invariants, which come from geometry. You can take the complement of the knot, and that is actually what's called, it's usually a hyperbolic space. It comes with a certain geometric structure. It has a notion of distance, and you can keep it as volume and some other invariants. And so these are invariants that are real or complex numbers. And so every knot comes with some combinatorial invariants, like signatures, and it comes with these geometric invariants, like these hyperbolic invariants, like, oops. So here is a whole list of knots with various of the hyperbolic invariants. There's something called the hyperbolic volume and the homological cusp shape and so forth. And these are real and complex numbers. But no one knew of any link between these two. So there are these two separate ways to create statistics of knots, and there was no connection between them. So it was only very recently that people started using machine learning to attack this problem. So they created databases of millions of knots, which actually was already a slightly non-trivial task, and they trained a neural network on this. And they found that after training the neural network, you could give it all the hyperbolic geometry invariants, and like 90% of the time, it will guess the right signature. So it created this black box, and it will tell you how the signature was somehow hidden somewhere in these geometric invariants. But it didn't tell you how. It was this black box. But that's still useful, because once you have this black box, you can just play with it. So what they did next is actually a very simple analysis. It's what's called saliency analysis. So what this black box does is it takes about 20 different inputs, one for each hyperbolic invariant, and produces one output, the signature. So once you have this black box, you can just tweak each input. You just say, oh, what if I change one input? How likely is it to change the output? And of the 20 inputs that they found that only 3 of them actually had played a really major role in the output. The other 17 were barely relevant. And it wasn't the 3 that they expected, actually. They expected the volume, for example, to be very important, and the volume turns out to be almost irrelevant. There were 3, something called longitudinal translation and the real and complex parts of meridional translation. So there were these 3 invariants that were the most important. So once they identified the ones that were most important, they could just plot directly the signature against those 3 particular inputs, and then they could eyeball rather than use a neural network. They used a human network to then see, oh, okay, there's some obvious patterns here, and so by staring at these graphs, they could actually make conjectures as to what was actually going on. So they made a conjecture based on this, which turned out to be wrong, actually, but. They actually used I think they turned back to the neural network to actually show that it was wrong. But then the way that it failed, they could correct it, and they found a corrected version of their conjecture, which actually did explain this phenomenon. And then once they found the right statement, they were able to prove it. So they actually have a theoretical explanation of why the signature is so closely related to these particular statistics. So this, I think, is a way in which machine learning is being increasingly used in mathematics. It doesn't directly solve the problem for you, but it gives you all these really useful hints as to what the connections are and go where to look for them. But you still need the human to actually make the connections. And then finally, we have the large language models, which are the most splashy and made the most news. Neural networks have been around for 20 years, language models have already also been around five or so years, but they've only become sort of human level in output very recently. So you've all probably heard of GPT-4. This is ChatGPT's current model. Very famously, when GPT-4 came out, there was a paper describing its capabilities, and they fed it basically a question from the 2022 IMO. There's a slightly simplified version. If you studied the 22 IMO, you probably don't. It's not exactly the same form, but it's a simplified form. And for this particular question, actually, you give it the question, and it actually gives a complete correct solution to this question. It actually solved an IMO question. Unfortunately, this is an extremely cherry-picked example. I think they tested hundreds of IMO level questions, and I think they had a success rate of about 1%. So this particular problem they were able to solve, and they had to format the problem in the right way to get the solution. But still, this is quite amazing. On the other hand, the funny thing about these tools is that things that humans find difficult, AI can do very easily sometimes, but things that humans find easy, AI often struggles with. It is a very orthogonal way of solving problems. In a very related paper or presentation, they asked the same model to do a basic arithmetic computation, 7 times 4 plus 8 times 8. And the model, which is just guessing the most likely output based on the input, basically just guessed, the answer is 120. And then it paused and said, okay, maybe I should give an explanation why it's 120. So they did a step-by-step. But when they did a step-by-step, they actually arrived at the actual answer, which is 92, and not the answer that they originally started with. So then if you asked, wait, but you said that it was 120, and they said, oh, that was a typo, sorry. The correct answer is 92. So they're not solving the problem by first principles. They're just sort of guessing at each step of the output what is the most natural thing to say next. And the amazing thing is sometimes that works, but often it doesn't. And it's still, it's still ongoing how to sort of make it more accurate. So people are trying all kinds of things. You can connect these models to other more reliable software. In fact, you will see a presentation after where there's a large language model connected where you don't do the computation yourself. You outsource it to Python in that case. But another thing you can do is that you can force the language model to only produce correct answers by forcing the model to output in one of these proof-assistant languages. And if it doesn't compile, you send it back to the AI, and the AI has to try again. Or you can try to teach it directly the same problem-solving techniques that you use to solve IMO problems. Try simple examples, proof of contradiction. Try to actually prove step by step and so forth. So people are trying all kinds of things. It's still nowhere near. Well, okay, we're not near able to solve a large majority of, say, Math Olympiad problems, let alone math research problems. But we're making progress. Besides being able to actually solve problems directly, it's also useful to just as a muse. Actually, I've also used these models myself. I've experimented with various problems. I had a combinatorial problem, which I was trying a few things and they weren't working. So as an experiment, I just tried asking GPT, what other techniques would you suggest to solve this question? And it gave me a list of 10 techniques, of which like 5 of which I'd already tried, or were obviously not helpful. A couple were not helpful. But there was one technique I'd not tried, which was to use generating functions for this particular question, which once they suggested it, I realized it was the right approach, but I had missed it. So just as someone to converse with, it is somewhat useful. It is not great right now, but it is not completely useless. there's another type of AI assistance that actually become very useful for proof assistance, actually. As I said, writing formal proofs is a very tedious task. I mean, it's like any really fussy computer language. You have to get the syntax exactly right. If you miss a step, it doesn't compile. But there are tools, so I use something called GitHub Copilot, where you can write down half of a proof, and it will try to guess what the next line is. And about 20% of the time, it actually guesses something close to being correct. And then you can just say, I'll accept that, and say, OK. So in this case, I was trying to prove the statement here, and the lines in gray are the ones that Copilot suggested. It turns out the first line is useless, but the second line, which you can't quite see, actually did solve this particular problem. So you still have to, you can't just accept, can't accept the input because it won't necessarily compile. But if you already know sort of how the code works, it saves you a lot of time. So these tools are getting better. So right now they can maybe, like if a proof is 1 line or 2 lines long, they can fill it in automatically. There are now experiments to sort of iterate an AI suggesting a proof, and then you feed it back to the compiler, and then if it compiles wrong, you send the error message back, and we're beginning to sort of proofs that are like 4 or 5 lines long, they can begin to find by this method. Of course, a big proof is like tens of thousands of lines, so it's nowhere near the point where you can just sort of instantly get your proof formalized immediately, but it is already a useful tool. Okay, so where are we now? So there are people who are hoping that in a few years we can use computers to actually solve math problems directly. I think we are still a long way away from that. For very narrowly focused problems, you can sort of set up specialized AIs to handle just a very narrow band of problems, but even then, they're not fully reliable. They can be useful, but still, So for the next few years, at least, they're basically going to be really useful assistants, and beyond the sort of the brute force computational assistance that we are already familiar with. And people are trying all kinds of creative things. I think one direction which I find particularly exciting, hasn't really been successful yet, is that hopefully these AIs will become very good at generating good conjectures. I mean, like so we already saw a little example of this with the knots, where they could already sort of conjecture those connections between two different statistics. So there's just the hope that you just create these enormous data sets and feed them into an AI, and they will just automatically generate lots of nice connections between different mathematical objects. This hasn't really been, we don't really know how to do this yet, partly because we don't have these massive data sets. But I think this is something that would eventually be possible. One thing I'm also excited, this is a type of mathematics that just doesn't exist yet. Now, right now, because proving theorems is such a painstaking process, we prove one theorem at a time, or maybe 2 or 3 if you're efficient. But with AIs, you could imagine in the future, instead of trying to solve one problem or something, you take a class of 1,000 similar problems, and you say, okay, you tell your AI, try to solve these 1,000 problems with this technique, and it will report back, I could solve 35% of these problems with this technique. What about this technique? Then I can solve this percentage of problems. Well, if I combine them, I can do this. You could start exploring the space of problems rather than just each problem separately. And this is something that you either cannot do right now, or you do over a process of decades with dozens and dozens of papers, slowly figuring out what you can and can't do with various techniques. But with these tools, you could really do. I mean, you could really sort of start, doing mathematics on a scale which is really not really unprecedented. I mean, the future is going to be really exciting, I think. I mean, we will still also be proving theorems the old-fashioned way. In fact, we'll have to, because we won't be able to guide these AIs unless we also know how to do these things ourselves. But we'll be able to do lots of things that we can't do right now. Okay, I think I will stop there. So thank you very much. Yeah. So we are on a tight schedule, but I was told we have time for maybe 3 or so questions. So if people would raise hands, and there's someone over there.
Thank you. Can you hear me? Thank you. That was a beautiful talk. I particularly loved about formalizing mathematics. But one thing that you didn't mention was Velikovsky, who left algebraic geometry because he made a mistake and started formalizing homotopy type theory. I would be interested to know if you have studied this and have any comments on it.
Right. Yeah, so Velikovsky, he was worried about a crisis in certain areas of mathematics, including some that he created. The proofs were so abstract and sophisticated that there was no way to verify that they're completely true. So he proposed changing the foundations of mathematics to homotopy, a higher order type theory, homotopy type theory, which is more robust. Like, if you change the underlying axiom of mathematics, a lot of what you prove in this theory is still true. There are proof-assistant languages that are based on this sort of homotopy type theory. Lean is not actually by design, because Lean wants to formalize a lot of traditional mathematics, which is not written in this language. I do hope in the future there will be multiple proof-assistant. There are multiple proof-assistant languages with different strengths and weaknesses. One thing that is not we don't have right now is automatic ways to translate a proof in one language to another. That's actually one place where AI, I think, will be very useful. Once we have that, then we can if you have a different philosophy of your foundation of mathematics, hopefully we can just translate a proof that has been formalized in one language to another, and then everyone will be convinced, including Velikovsky if he was still alive, hopefully. So there are multiple approaches to formalizing mathematics, and we shouldn't just fix on one particular standard just yet. Okay. It's sort of a random process, but okay.
That will not be quite relevant to the topic of the talk. But I was recently applying for PhDs, and the advice I was given by the professors was basically along the lines of the longer the better. So it seems like there's kind of a general agreement that mathematicians need somehow it would seem to me, grow up to big ideas. So from that perspective, how do you think about your decision about going to the university at such a young age? Did you think how it influenced you as a mathematician and as a human being? And
I had some very good advisors, both at the high school and undergraduate and graduate level. I don't think it's a race. You go to university when you're ready to go. You shouldn't go just because you were told you need X years or something to do this. I think it's different for different people. It was very important for me. I went to undergraduate when I was 13. But but at a university that was very close to where I lived. So I lived with my parents, and they drove quite a lot actually to the university for all my classes. If I didn't have that, I don't think I would have had a good experience. So it really depends. I did my university at a very young age. Doesn't mean that everybody should do that. There's no single answer to this question.
Thank you.
Okay.
So another kind of more general question. Given that you've contributed to truly myriad mathematical fields, how do you go about choosing your next research topic and problem you want to solve? And also, what's your IRDAS number?
Okay, well, my IRDAS number is 2, that's easy. But I actually don't know. Early on in my career, I had advisors who would suggest problems to me. Nowadays, often it just comes by serendipity. Math is a very social activity. You go to lots of events. So, after this, I'm going to a math conference in Edinburgh. I'm going to talk to a lot of people in actually area connected to this PFR conjecture thing, actually. And likely I'll have some interesting math conversations and maybe some research question will come out of it. I do have some long-term projects that I would like to, something that I'd like to solve, but increasingly I find that it's the questions that just sort of come up by conversation with other mathematicians. I didn't know I'd be talking so much about AI until about 2 years ago, for instance. I think it should be sort of, the future is going to require more flexibility, and there will still be people who will specialize in one topic and just one topic and be the world expert in X. But increasingly, I think there will be more and more people who will move around over time and just they will find interest in new mathematics every few years just by talking about people. Okay, I think we have to move on actually. So the next speaker is Simon Coyle from XDX, who will talk about the AI Math Olympiad.